Welcome to this 101 lesson on resistance, focusing on basic properties of resistance, some circuit problems, and looking at resistance bands. Resistance is the opposition to flow. It's measured in ohms, named after this famous bloke behind Ohm's Law. Consider the analogy where my dog represents the flow of current and the yard here represents a typical wire. As we can see, she moves quite freely from the positive to the negative end of the wire. This in practice, however, is not always the case, and typically wires contain impurities that resist and oppose the flow of current. This is resistance. Adding some obstacles to my yard, this should slow down the movement of my dog, in theory at least. My dog's acrobatics offer a chance to explore some other important concepts closely related to resistance. Her reluctance to go anywhere near the buckets, but willingness to jump over the planks or garden for that matter, relate closely to the current divider law and the concept of shorting a circuit. These are both massive topics in their own right and should be left for another video, though it is worth noting that they are both underpinned by the concept of taking the path of least resistance. Back to the original point of this backyard experiment, the resistance of a wire can be given by the following expression, where ρ represents the resistivity measured in ohm centimeters. Length is also directly proportional to resistance, and as the length of a wire increases, so too does its resistance. Looking to the denominator of this expression, we can see that area is inversely proportional to resistance. What this means is, as we increase the area of a wire, its resistance is going to decrease. Smaller wires mean more collisions and therefore greater resistance. Finally, the delta T value represents the change in temperature from 20 degrees Celsius. As temperature increases, so too does resistance. There are some essential equations we require when solving resistance problems. Resistors in series are summed as shown. When in parallel, we consider the inverse of the resistance values, and the product sum rule is a special equation we can apply for two resistors in parallel. Let's quickly consider some example problems. This question asks about the effect of doubling the area of a conductor. And looking to our equation, we can see that times in the area by 2 is going to halve the resistance and therefore cut the resistance in half. Now for this problem, pause and have a go yourself. But basically, we can step through it using our series and parallel understanding, marking where we see series and parallel relationships. We arrive at this equation for the total resistance, which, when we apply our formulas, will look like this. An equation like this avoids any potential rounding errors, and hopefully you found the solution, 128.8 ohms. Let's now consider resistors and resistance bands. There's a handy mnemonic involving this guy, that black bears run on your garden, but veggies grow well. This corresponds to the colours that you'll find on your resistor chart, though some might find it just as easy to keep one such chart handy at all times. Ultimately, it's whatever works for you. If you're keen to learn more, check out these awesome videos, links are in the description.